Welcome back, students. Welcome to our YouTube channel. As you know that we are studying about integral transform, in which we are studying about the beta and gamma function. We are about integral transform, in which we are studying about the beta and gamma function. We have seen the definition of beta function and gamma function, in which we have beta function as two variable function, and we consider that variable as mn, and we have the definition integration from 0 to 1 x raised to m minus 1 1 minus x raised to n minus 1 dx. Correct. Similarly, we have gamma function m and n are correct, and we have gamma function defined as integration from 0 to infinity x raised to minus t raised to n minus 1 dt. Correct. e raised to minus t into t raised to n minus 1. It is the definition of gamma function. Correct. Or if you want to write in variable x, so we can write it as e raised to minus x raised to n minus 1 dx. So you can change variable as per your convenience. Today and after that, after knowing the definition of and formula for beta and gamma function, we have studied about the different or elementary and basic properties of beta and gamma function in previous lectures, and we have seen the different transformations of beta and gamma function, and we have seen some examples based on beta and gamma function too. But today we are going to see the type of example which is based on integration beta mn is equals to integration from 0 to infinity x raised to m minus 1 1 plus x raised to m plus n. We are going to see the examples based on this property, which is integration from 0 to infinity x raised to m minus 1 upon 1 plus x raised to m plus n dx. Correct? It is a form of beta function in which we have x raised to m minus 1 in numerator, and in denominator we have 1 plus x raised to m plus n. Correct? So let's see the example based on such form. An example is as follows: integration from 0 to infinity. Integration from 0 to infinity. We may consider this is as I. Integration from 0 to infinity x raised to 9. X raised to 9 1 minus x raised to 7 upon 1 plus x raised to 27. 1 plus x raised to or bracket raised to 27 dx. Now we have one example which is we are going to be solved. And the example is given as follows: integration from 0 to infinity x raised to 9 into 1 minus x raised to 7 upon 1 plus x bracket raised to 27 dx. And since we know that the form of beta function, beta of mn is equals to integration from 0 to infinity x raised to m minus 1 upon 1 plus x raised to m So we can simplify this integration I into two different integration I1 and I2, and which is as follows: integration from 0 to infinity x raised to 9. When we multiply x raised to 9 into this bracket into 1 minus x raised to 9 into x raised to 7 upon 1 plus x raised to 27 dx. Correct? We have just multiplied x raised to 9 into this bracket, and after multiplication x raised to 9 into 1, we will get integration from 0 to infinity x raised to 9, and we have x raised to 9 plus 7 and 1 plus x raised to 27 dx. Since we know that a raised to m into a raised to n is equal to a raised to m plus n. We studied this property in previous classes. If we have base same and power, when these terms are in multiplication, we add the power of that base. So we have x raised to 9 minus x raised to 9 plus 7. So I will be integration from 0 to infinity x raised to 9 minus x raised to 16 1 plus x raised to 27 dx. Correct? And we can simplify this equation by x raised to 9 1 plus x raised to 27 dx minus x raised to 16 1 plus x raised to 27 dx. Correct? And we have two different expressions in integration, and we know that linearity property holds in integration. So we can write this equation as integration from 0 to infinity x raised to 9 1 plus x raised to 27 dx minus integration from 0 to infinity x raised to 16 1 plus x raised to 27 dx. Correct? Now we have two different integration, in which one is integration from 0 to infinity x raised to 9 upon 1 plus x bracket raised to 27 dx, and another is integration from 0 to infinity x raised to 16 upon 1 plus x bracket raised to 27 dx. Now, since we are studying the type 1, which is beta of mn is equals to integration from 0 to infinity x raised to m minus 1 upon 1 plus x raised to m plus n dx. Correct? So we try to put this numerator x raised to 9 in the form of x raised to m minus 1, and if we want to convert this 9 into m minus 1, so we can write it as x raised to 10 minus 1 m minus 1. Again 10 minus 1 means 9, correct? And m plus n, where m is 10, so we can write it as x 1 plus x raised to 10 plus, and here 27, so we can write it as 17. Correct? 10 plus 17 dx. Similarly, we will convert this equation to, and which will be x raised to 17 minus 1 and 1 plus x raised to 17 plus, and we want 27 means 10 dx. So we can write this integral in the beta mn form. So we can write this form as beta of 10 comma 17 minus, as it is, beta of 17 comma 10. And since we know that beta is symmetric, therefore beta of mn is equals to beta of nn. Therefore beta of 10 comma 17 is equals to beta of 17 comma 10, both are equal. Therefore beta 10 comma 17 minus beta 17 minus comma 10 means equation A. Therefore equation A will give us 0. I equals to 0. This implies that integration from 0 to infinity x raised to 9 1 minus x raised to 7 upon 1 plus x raised to 27 dx is equals to 0. And it is the required result for this example. In this section we are studying about the application of beta function, especially on the type 1 form, in which we have beta mn function, beta of mn function defined as integration from 0 to infinity x raised to m minus 1 1 plus x raised to n plus n dx. By using this form or transformation of beta function, we are solving the same form of example in this type, and we have the result as 0 for integration 0 to infinity x raised to m into 1 minus x raised to 7 upon 1 plus x bracket raised to 27 dx. So we will continue such type of example in next lecture. Till then, thank you.